Recording is rolling. It is Tuesday, August 26th. We're going to continue this current incline the graphs and equations. All right, AP, you guys had your lab write-ups out. We're going to score those together in class. You guys got a color pencil on your desk. So we're going to do this. I like to do this a lot of times. It's give you guys a model AP write-up that I put together. It's pretty close to what AP would actually like how they would score it if they give you this question. Okay, so you can have that in front of you. You can see exactly what you wrote and what the rubric would say, and you get a point. So go over those. I have some linear motion demos we're going to get to, and we start puzzles here. You guys remember Friday? I'm going to throw a quiz at you guys. It's just going to be on anything that you guys see in this class up to this day. Okay, so a bit. All right, so see. Filling in here. You guys are taking these Hot Wheels cars. You guys were rolling down the incline. Well, release from rest. So you release it from rest, rolls down the incline, does something like this. We're trying to figure out what equation or equation could govern the motion of this car. All right, we had all these variables we were keeping track of. Like, how does the mass of the car affect the motion? What's the relationship between how far it rolls and how much time it's been rolling for? This versus time. Ooh, what if we bring in speed? Speed versus time, speed versus distance. Huh. Okay. What else going to look like? And we did some of these yesterday. Right, so I've got to recap the far. Forget if this was exactly your class or a different class, but all the graphs basically look the same. It's graph mass versus time. So I see lots of different mass cars here, right? 5 different mass cars because you got to take around the slab weights. Okay. And look, it's like the same time over and over and over. It's like 2.5 seconds to reach the bottom, regardless. And of course, controlling for the rolling distance for that. Okay. Guys, what did that mean? That meant how does mass enter into these equations?
It doesn't matter.
Yeah, doesn't matter. You can say there's no relationship between mass and rolling time. Yeah, so the mass is actually not going to be part of these kinematic equations. Okay. I had you guys roll. Well, if you had the spades, you said what's the relationship between distance and time? Okay, and then if you plot it, like how far the car rolls, a function of how much time it's been rolling for. Okay. Now this one could be a little tricky because if you just have these 5 points and nothing else, at a glance, I say, well, is that a linear relationship? Because it almost looks like I can take my roller, zip, line best fit. Okay. You think, well, hold on, logically 0, 0 should be a point, and you could empirically grab that too, or grab values close to here. Wait, a better fitting curve is actually what turns out to be a parabola shape. So suppose you had a hunch or suspected that, or logically you realized, oh, it couldn't actually be linear because it got this intercept that didn't make any sense. Okay, and I'm reiterating all this because guys, you're going to see this in future labs too, right? This is a common thing to see. Right, so say, hey, what if I graph not x versus t, but x versus t squared? What would that look like? And that ends up looking like this: x versus t squared. Now, this is a manipulated axis. The unit for time squared is square seconds. And so this is an abstract idea. But conveniently, all the points now line up in a straight line. This is a direct relationship. And that's much easier to create an equation out of because you can just grab the slope, rise over run between 2 points on the line. And then now you have your slope. You just do vertical axis equals slope times horizontal axis. Boom. Okay, so that question. Now, guys, see if you guys are following. You guys see this x equals 24 centimeters per second squared times the time squared. Okay, which represents the straight line right here. Does this equation also represent this parabola? Is it the exact same equation? Who says it is? Who says it is? It's the exact same equation. If you're raising your hand, some of you guys are, then you are correct. Yes. Guys, this equation here, x equals 24 centimeters per second squared t squared, to describe this straight line, also describes this parabola because they're on different sets of axes. This is x versus t squared. That's why it lights up a straight line. This is x versus t. That's why it goes like a parabola. Okay, remember that? All right, and then what else we got? So here's the last one we fit in for the bell yesterday. Some of you guys had speed gates at the bottom of the incline, and the car would zip down. I said, well, what's the speed at the end? So I should really throw a subscript F for final velocity because they're different kind of velocities, right? So the car started from rest, right, and it was going faster. We're talking about the speed at the end of that motion, at the end of that interval. Okay, so in this case, at the end of a time interval. Okay, and these points all align in a straight line. So could you make an equation out of this to something like v equals the slope times t? Okay, and it turns out that the slope of this graph is the acceleration of the car. That's to say the rate that it's speeding up. Right, and then the bell rang. So we have one more category to go through. All right, this guys, who had the hearts in here? Who had the hearts? All right, you got. All right, so Lily, gonna have you share some data. Got some good data there. We're gonna see speed versus distance. Right. So, and everybody else is also making this graph, the one that says v versus x. Right. So, how fast is a function of distance? Right. Remember, how fast is a function of time was linear, but I remember distance and time are not linear. Right. There's some kind of parabola. I'm already suspecting this is going to be a parabola shape, or maybe I'll throw a subscript f, like final velocity, as a function of distance rolled. So get some axes set up here. Axes. Okay. Um, Lily, what was your fastest reading? Your fastest speed?
163.
163. Okay, so it sounds like final velocity is going to be in centimeters per second. Okay. And maybe I'll scale this up to 200. Let's go 50, 100, 150, 200. So 0, 50, 100, 150, 200. Okay. You guys know to start your axes at 0 and then scale linearly and stuff. Okay. And what was your furthest rolling distance?
222.
222. So looks like x would be in centimeters. Right. Okay. So that's good consistency, right? So centimeters and centimeters. Okay. So 200 something. So let's go, how about 50, 100, 150, 200, 250. That's pretty good. So 0, 50, 100, 150, 200, 250. All right, so let's get some. Right, and what should this sort of look like? Right, you might be able to do some algebra substitution based on what we did yesterday and kind of figure this out. Okay, but let's do some quick hypothesizing. Like the further the car goes, we think it'd be going faster. Right, but how faster? It's going to be linear like this. It's going to be the parabola like this, or it's going to be like a square root relationship, which is also parabola just on its side. Okay, show hands. How many of you guys think it's going to be direct relationship? Who thinks that? Who thinks that? Who thinks that it's going to be a parabola like this way? That's to say, double the distance would be 4 times the speed. Who thinks that? Right? And who thinks it's going to be a square root this way? That's to say that 4 times the distance would only be double the speed. Who thinks that? Ooh, okay. So I'm seeing votes on all those. We're going to find out. Right, so Lily, what's one of your coordinates?
The speed was 78.1.
So 50 centimeters, 78.1. It's about right there. So you got 50, 78. This would be centimeters per second. All right, next one.
100, the speed was 107.1.
You said 100 what?
107.
107.1, 107. It's about right there. Okay, so I got 100, 107. So it's centimeters per second. All right, next one.
At 150, it was 136.6.
136.6. Okay. 150, 136, centimeters per second. All right, next one.
At 200, it was 157.3.
157.3. 57. Right there. So 200, 157.3 centimeters per second. All right. And at this point,
At 222, it was 163.7.
222, 163.7. It's about 222, 163.7. Okay, centimeters per second. Okay. All right, so you guys getting that too? Okay. So go back to this right here. Guys, which category graph does that look like? Yeah, definitely this root right here, right? Looks like this root. Okay. So also you could sort of logically figure out 0, 0 should be a point. It hasn't rolled anywhere, hasn't picked up a speed yet, like at least from us. Okay. Or you could empirically grab that. But yeah, it looks like some kind of root relationship. Okay. Sometimes at this point students say linear, they go, oh look, all those points, it looks like they lie on a line, right? But then if you extrapolate back to the axis, it's that would be like if it hasn't gone anywhere yet, it's already has a speed, like kind of like you gave the car a push, which was not the case because you released it from rest. Yes, it's got to be this. Okay. Remember what this means proportion. Well, if this really is the speed it picks up to is proportional to the square root of the rolling distance, because that's what it looks like, right? What if you threw a factor of 9 on that distance. Say we went from 10 to 90 centimeters. That'd be 9 times the distance. Guys, 9 times the distance should correspond to how many times the speed? 3? Yeah, because that would be a square root, wouldn't it? So 9 times the distance should be 3 times speed. Okay. But let's say if that's true. We're also going to linearize this one. Now, we linearized a different graph yesterday because we went from x versus t to x versus t squared. There is x versus t squared, right? That linear. Now, what do you think you have to do to linearize this graph? What's one way? Okay.
You like square the x.
Okay, I don't want. How about
Yeah, that's what it
what's that?
would you square find the velocity?
Yeah. Okay. Actually, there's 2 ways to do it. You can either take the square root of the rolling distance, which we're not going to do. That should linearize it. Or yeah, you could square the final velocity. Like guys, if I take this proportion, guys, this is like a proportion sign. So it's like sort of like an equation, but I'm leaving out parts of it. Okay, maybe there's more going on. Right? What if I square both sides? Can I say b final squared is proportional to the rolling distance? Okay. So either of these could linearize it. Thanks. It's going to bring us to last graph we're all put together right here. Last graph. All right, so we're going to go. You got relocated here. Yeah, you can just separate them. All right, so we're going to go final velocity squared versus the rolling distance. So final velocity squared versus the rolling distance. Right. Lily, did you square all the speed there?
Yes.
All right, so what's the fastest speed squared?
It was 26,000.
Okay, so we're doing centimeters per second, collectively against squared. We got 26,000. So let's go about 5,000, 10,000, 15, 20, 25, 30,000. So, oh guys, what's the prefix for 1,000?
K.
Yeah, K, right? We can do 5,000, then 10,000, 15,000, 20,000, 25,000, 30,000. And then now the rolling distances would be the same. So I can just copy paste that axis. That'd be in centimeters here. And this could go 50, 100, 150, 200, 250. So 0, 50, 100, 150, 200, 250. Okay. All right. This should linearize. Well, let's see if it does. Because if it does, then what that means is that our hunch that this was truly a square root would have been correct. And furthermore, we can get an equation out of this. All right, so what's one coordinate here?
50, it was at 6,000.
50, 6,091. So 50, 6,091. Okay, yeah, these would all be in centimeters and centimeters per second collectively being squared. All right, let us get
100 was 11,470.
11,470. So 100, 11,470. Okay.
150 was 18,659.
18,000. Okay, so there's 150. He said 18,000 what?
650.
Yeah, so pretty close there.
200 was 24,743.
24,000. Okay, so 200. Said 24,000 something.
Yes.
Okay. All right. And fifth point.
222 was at 26,797.
26,000. 222. 26,000. Something right. Yeah. Okay, something like that. Yeah. All right. Guys, does that create a direct relationship? Sure does. Look at that. Right, so you do line best fit, zip. Right. Let's make an equation out of this. Right, so I can say the final velocity picked up 2 squared equals, right? Now, notice I got rid of the proportion sign and substituting in equals. So I need the slope, like the rise of a run. Okay, so let's put 2 points on the line. Looks like actually this coordinate and this coordinate pretty well go through. So maybe I'll just do rise or run between those two. Go slope. Okay, so that'd be a change in 24,000 minus 671, all divided by then 200 minus 50, 150. Okay, I'm getting like 119 some. Now this would be, let's see, centimeters per second collectively being squared, all divided by centimeters. Right? Or I could just call that very simply centimeters per second squared. Yeah, same thing. Right? And that's how you can complete this equation. So 119, this would be centimeters per second squared is the unit, then times x, where x would be in centimeters. Yep. And that right there will describe how fast the car is moving after some distance interval. Ooh. Right, guys good? Yeah. All right. I think I did this yesterday. I was peeking ahead to where this is all leading. Because this is related to this bottom formula right here. So remember, V naught, the initial velocity, which if you lose the car from rest, that's just zero, right? So I can just get rid of this term right here. Okay. So speed squared should be equal to 2 times the actual acceleration, which is right, the car speeding up, times the distance. Okay. So it looks like this 119 number here, centimeters per second squared, represents what? 2 times the acceleration, right? You guys see 2? In place of this 2a, isn't this 2a? Isn't that equal to this 119 number? You guys get it? That takes the place right here. So in place of 2a, I have 119. So let's take advantage of that and figure out, well, what would the acceleration of the car then be? So 2 times the acceleration of the car would be 119 centimeters per second squared. Okay. By the way, what I'm doing right now, AP could totally ask this question, like as an FRP. So could you just divide both sides by 2? Was that 59.5, I think, something like that? 59.5 centimeters per second squared, or about 60 centimeters per second squared. Right? And then many weeks in the future, we'll be doing this, right? Which is the same model as what you guys did. Okay, so G sine theta. Lily, what was your angle at incline? 5 degrees. Let's say it is. Does anybody remember what pure free fall is on Earth? This G. Yeah, 9.8 meters per second squared, which is, of course, also an acceleration. It's a pure free fall. If I do sine 5 degrees, it gives me about 0.85 meters per second squared. Could you call that 85 centimeters per second squared? 85 centimeters per second squared. Now, keep in mind too, this is like an upper boundary because realistically, you guys did have a little bit of friction, maybe slowing stuff down too, right? Okay. So 85 centimeters per second squared would be the upper boundary. That should be pretty close to that. You got about 60. Yeah, it's like right in the ballpark. So exactly what it looks like. Yeah. All right, doing good. Right. So let's do let, let's do this. I want to do equations with you guys, and then let's score the rubrics after the fact. Right. So let's do these equations. Because guys, these 3 kinematic formulas, you're going to be the rest of the class all the way through May. Right? These are never going away. In fact, if you're going hard science engineering in college, and these are never going away, you're alive. These will always be here. Right? So now these are all in a linear context, but you can also go into 2 and 3 dimensions. So we'll eventually also use these same 3 for projectiles and so on. Right? So let's make sense of this. I'm actually going to start with this middle one, sort of like derive this and then branch out and show you guys how this all connects. Okay? So let's look at the definition of acceleration. So acceleration is the rate change in velocity. Okay. Actually, I should back up right before that too. Let's go over all the characters that you even see on this page. Like x is a variable, t is a variable. Okay. Guys, if you keep in count, how many unique variables are even on this page?
Like
5 if you count the different velocities. Right? Okay. So here, let's do, sometimes I call it tax speed, the time, acceleration, displacement, initial velocity, final velocity. Okay, just to be modernized. So t is time. That's going to be counted in this class in seconds. Let's skip down to this x for displacement. Okay. In this class, normally we go to unit going to be in meters. Now, v is for velocity, like speed, but sometimes there's a direction implied, sometimes specified. So I have initial velocity. Guys, what's the unit for velocity in this class? Yeah, meters per second. Okay, kind of like miles per hour, same concept, but meters per second. Yeah. Okay. And when you guys were releasing your cars from rest, what should this number come out to be? Yeah, 0. Okay. And then VF would be final velocity. So that would also be, of course, meters per second. That's how fast it's going at the end of some interval. Because these are instantaneous velocities. These are not average values. Okay. All right. So these are, yeah, I'll specify that. Instantaneous values. If you talk about average velocity, it's like total distance over total time. We might do that a little bit in the future, but normally I'm talking about these instantaneous values. If you point a radar gun, how fast it's going. And this A is acceleration, which we're about to be looking at here. So this would be meters per second squared, because it's meters per second per passing second. Okay, it's how fast are you changing your velocity. So if you're in the car, you slam on the gas pedal, you're speeding up. Or if you slam on the brake, come to a stop. That's also a type of acceleration. Negative acceleration, deceleration. Okay, you guys got this? Right, so let's look at acceleration then. Let's come up with a little expression for this. Now, if I spell it out like this, is this okay? Like rate change of velocity? Okay. Right, so when I say rate change, I'm talking about some fraction, right? Something relative to something. Right. I want to see if you guys can figure this out based on everything you've done in this lab up to like this moment. Okay, can I come up with a little expression, maybe from scratch? Right. What do you think is sort of a definitional expression for acceleration in terms of variables? Okay, yeah, it's going to be in meters per second squared. So something to do with like meters per second squared. Guys, can meters per second squared be meters per second per passing second? Right, as units, isn't that meters per second squared? Okay. Maybe that's a hint as to what this formula should look like in terms of variables. Good. Oh, here, if your car's speeding up, has some initial velocity here, has some final velocity here, maybe like a little velocity arrow. Okay. And let's say it took some amount of time to go from here to here. Let's just use in terms of time because time can be in the seconds right here. Okay. Guys, if I say rate change of velocity, am I talking about a change in velocity per unit time? Right? Here, I'll throw in a middle step. So sometimes you see it written this way. Change in velocity. Isn't that what the delta is? Like a change velocity per time interval. Sometimes you see a delta t like time interval. Sometimes just t. Right? Right. But in terms of these characters, the initial and the final velocity, I'm gonna modify this one more. Gonna go acceleration is. Guys, can you in place of this delta v, can you write that in terms of final and initial velocity? What would that look like? How about the difference, right? Final minus initial, right? And then the t, well, delta t, I'll just call it t. Okay, like a time interval. Okay. Wouldn't it be true, guys? It isn't the change in something; it's final value minus its initial value. Isn't that like the change, right? Again, you guys were starting cars from rest, so your V naught was 0 for your lab, so something like that, right? Okay. Now, okay, you guys got that? Okay. Okay. Let's do a little algebra rearrangement. I want to solve for this V final. Yeah, just for fun. Let's see what happens. Well, actually, more than just for fun. All right, give you guys a head start. Can you guys do a little algebra? Do a little algebra. Giving you guys a head start. Solve for that V final. Okay, so we're sort of from the definition of acceleration. It's a rate change in velocities. Okay. Guys, all in terms of letters. There's no numbers. No numbers. You're doing algebra, all in terms of variables. Yeah.
You can have every formula.
Okay, yeah. So you guys know I'm building up to these 3 kinematic formulas. The question is, do you have to memorize the formulas that we're building up to, or is there a reference sheet? So there is a reference sheet. Well, for AP. Guys, when we take the AP exam, AP will give you this page. And the formulas we're building up to, they look a little bit different than the way I write them, but I'll go over that too. Okay. I do recommend that you eventually memorize these 3 kinematic formulas because they're really handy to know because it'll save you time. But yeah. Okay. So did you guys cross multiply the time? You get VF we're solving for minus V naught is equal to acceleration times time. That could be one step, right? Okay. And what's the next step? Can I add over the V naught? So V final equals V initial plus AT. Is that true? Is So it'd be like that, right? You guys see it? Right. And what you guys just did then is starting from this definition of acceleration and combining it with some algebra, you see you just effectively derived this middle formula right here, right? That's exactly what it said. Just a little bit different way of looking at it. It says how fast you go up. It's how fast you started, plus the rate that you're speeding up times however much time. That's all. Right? Or if you're slowing down, acceleration can be negative. Right? That's all. You guys can see how this connects to this? Right. Now, what about these other ones? These other ones look a little more involved, right? So I want to do this way. Yeah, I'll just show you guys the poster version of this. So I'll show you guys two ways to derive this top formula of how far is something gone. Because notice one, you drive so far, doesn't mention how far, say your car's moved. It only mentions like how fast and how much time, acceleration. Okay? But how do you get how far it's moved? Now there's a few ways to look at this. I'll show you guys a Paul Hewitt video later where he drives this algebraically a different way. Okay, but I'll do the graph way. Now guys, df equals v naught plus at. That's the last line in your notes. Does this look like y equals mx plus b? Just shift it around a little bit. Okay. And if you had a velocity versus time graph, ooh, look at that. Isn't this, where have you guys seen that go through? I think up here, nope, that's the wrong one. Here it is. Right. Isn't this from yesterday? Velocity versus time? Wasn't that also a linear relationship for a uniform acceleration? Okay. And this class, we're typically only working with what's called uniform acceleration. That's to say that this line will have a constant slope. Okay, that's it. Okay. Well, what if you gave the car a push? Could you more generally just say that's kind of like shifting this line up and down? Okay. Guys, if you give the car an initial push, that would be changing its initial velocity, right? Which is like changing its intercept. Does that change the slope of the graph if you give the car a push? No. Because once it's in motion, it's just going to accelerate however it's accelerating, something to do with Earth gravity and whatnot. Right? Earth gravity is related to the slope. Right. So stand back and look at this. So the acceleration, you guys see how the acceleration is on this graph? So the graph itself is just this black line. Right? The acceleration is defined as the rate change in that velocity, which is the slope. Right? That's acceleration. Okay. Which, you can just rearrange this, and that brings us back to, these notes you guys were just doing right here. Isn't that the same thing as this right here? Right. And there's another property of this graph. Right? How about this? Let's start real simple. I'm going to block off the top and just focus on this rectangle down here. Okay? Okay, suppose you're driving in a car and you're going 60 miles an hour and you do that for 3 hours. You're going 60 miles an hour for 3 hours. How far have you driven? 180 miles, right? And what'd you do with those numbers to get to that answer? Yeah, just multiply it, right? Right. So miles per hour times hours, right? Now, of course, we're using meters per second and seconds. Same concept, right? But do you guys see graphically that will work out to a rectangle? Because isn't the area of a rectangle the space inside? Right? So if you had a constant velocity, then how far you've gone would be represented by the area of this rectangle. Are you guys good with that? Okay. Now, it turns out that that's generally true regardless of the shape of the graph. So if you have any velocity versus time graph, the area under the curve represents the displacement. Right. Now, this is a general principle that's going to show up in a lot of other type of graphs. So let me show you guys in terms of units how these work out for the acceleration and for the distance. Okay. Guys, look at the units on the axes, because units are a big deal in this class. You guys see meters per second here and seconds here? Right? Let's divide them and say what unit does that give? Because if you divide, it's more like the slope. So what is meters per second divided by seconds? That's called what? Meters per second squared, which is an acceleration unit, which tells you that the slope of this might refer to the acceleration. Right? Now, what about the area? The area. Isn't the area something to do with base times height? Isn't that true? Right, base times height. And if the base is in seconds and the height is in meters per second, and I multiply that, what happens? What is that equal to? Meters. Is that just meters? Oh, and guys, what does meters measure? Yeah, distance or displacement, right? Yeah, typically, displacement in this class, like in case this car turns around and goes backwards. Displacement, yeah. All right, so meters could tell you, okay, do you guys see this big old green looking trapezoid? There's really a triangle sitting on top of a rectangle, isn't it? So do you guys see, I'm making the claim here, you guys can probably see where this is going, that if you add these two green regions together, this rectangle plus this triangle, should that be v naught t plus half at squared? Right? Wouldn't that be exactly this top kinematic formula right here? Okay. But I really, really want to convince you guys that this 1/2 AT squared is true. So let's go back to just the triangle bit, right? So the triangle bit right here. Okay. Okay. So I got some amount of time and seconds take along. Right. Let's say we'll just go back to starting from rest. We'll do velocity versus time. So put velocity in meters per second here. Right. And let's say I want to know like, how far is the car going. Okay. Okay. So that should be represented by this area here. I'll call this X for displacement. But what is that in terms of V and A and T? Okay. You guys remember the slope of this line, the slope of velocity versus time is equal to what variable? A, acceleration. That's the rate change of velocity. Okay. So can you get this final velocity up here in terms of this acceleration and how much time it's going to go for? I'll just call this final time t, or maybe this whole interval could be t. Okay. Okay. This is t. Guys, if this base right here is t, okay, and this acceleration is a, the slope is a, then what's this final velocity equal to in terms of a and t? A times t. Yeah, it's just a times t. Right? So I'll say the area of this triangle, which I'm calling x for displacement. Right? Oh, guys, what's the area of the triangle? It's what times what times what?
1/2 the base.
Yeah, 1/2 base height. Here, I'll spell that out. 1/2 base height. Right? And the base is some value t, and the height is a times t, isn't it? You guys see that? A times t. Right? Put it all together. X is 1/2 AT squared. As long as you start from rest, or if you just look at the triangle bit, it's 1/2 AT squared. Is that it? Is that? Okay. And that is going to be this top one right here. Right. So we drive this middle one first, then we move to the top one. Right. Okay. Now, what about this third one? And what are the specific applications of these? Okay. So, do you guys see that each of these formulas might be more useful in some context, depending on what information you have. Like the top formula, I see it has a bunch of variables in it, but it doesn't say anything about final velocity, right? So if you didn't have that, you weren't asked it, right? What was final speeds? Okay. This middle one doesn't say anything about how far someone's moved, right? And guys, what information is lacking about this bottom formula? It doesn't mention how much what? Time, yeah. Right. So if you're told how far something moves and accelerating and asked like how fast does it end up, but you're never told how much time passes, it's probably a good candidate for that third kinematic formula. Okay. I'm going to save us a little bit of time here. So you can, there's different ways you can get this bottom one. You can take these top two. Do you think you can take these top two as a system of equations and substitute out this time right here? Could you do that? Right. I did that before class just to check it, but maybe I'll save some time. So I'm going to throw this on the screen. If this really intrigues you and you want to try this out yourself, I would encourage you to do that. Right. But this is the proof right here, where you get down to the very last step is this third kinematic formula. Okay, so, right. So now you have a way to navigate these kinematic expressions. Okay. Here's another rule of thumb right here. Here's your 5 kinematic variables. So we got time, acceleration, displacement, initial velocity, final velocity, which are instantaneous values. Okay. Rule of thumb is if in any physics question you can identify 3 variables, the other 2 become solvable through those 3 kinematic formulas. Okay. And I have lots and lots of examples with those, like that. This page I gave you guys the other day is kind of set up that way with tables, and I identified 3, blah, blah, blah. Right? But sometimes there's a variable that's sort of hidden. Like, guys, if anything ever starts from rest, would you know initial velocity is equal to what? 0 meters per second. And they might not explicitly print a number. And you say, I only see 2 numbers. How can I solve it? Oh, I'll start from rest. Okay, I do know 3 things. Okay. Or, guys, what if something comes to a stop? What could that tell you? Final velocity could be 0 meters per second. Again, if you only see it, I only see 2 numbers. Oh, comes to a stop. Actually, I do know 3 things. Okay, so things like that. All right, let's score your guys's write-ups. Okay, so there should be a rubric on your desk. I think I got the suits right. I took all the cards off. Okay, so does the scoring rubric on your desk have the correct suit? Okay, all right, so pretty sure it did. Okay, so I have the spades here. This is for distance versus time. Now, this one I'll do on camera, but then I'll give you guys time to score your own. You guys have a colored pencil? You guys have a colored pencil? Okay. Now, the points here add up to 15 points, the same as on the APFRQ that you're going to get in May. Okay. So if you got this exact question, so something like this, like what's the relationship between distance and time for a car to roll down an incline at constant mass and constant incline angle, like that. Okay. So if you wrote the question, the relevant question, again, based on your suit, you basically have a question, give yourself a point. Okay. So I'll go through this down kind of fast just for the video, right? And then again, there's one for every suit. You guys got it's out here. Oh, also I did post these to Google Classroom yesterday, so there's a PDF with all these. Just go through one. Okay. So measuring tools. Well, you probably have all these measuring tools involved. Like you have a protractor, yes. You have a scale, yes. Okay. But for this particular lab, what you would get points for, and I know just by reading so many of these, is they definitely want you to mention the meter stick and the stopwatch. Or maybe a second timer because distance versus time. Oh, yeah. Lily, you have a question? No? Okay. Okay. Right. So that's what you would award the point. Like you have to mention those for sure because that's relevant to these variables.
We put speed gates and a motion detector. Is it the same thing?
Okay. Yeah. So for measuring the speed, yeah, that's good. Oh, do I not have one up here? Yeah. Okay. Yeah, I took all my tools off. No. So you good? No. I was looking for that speed gate. Yeah, guys, the speed gate. So you guys know that little speed gate that the car was going through? All right, so AP does not know what a speed gate is. So it's perfectly fine in this class. If you mention the speed gate, that is the tool you use. So yeah, you get credit for a speed gate. If you had to measure the speed using the speed gate, that's fine. Right? AP does not know. So AP graders would be totally confused, like, what's a speed gate? Right? AP graders do know what a motion detector is. So if you mention motion detector, you guys remember that little boxy thing I was saying works like a bat with echolocation or whatever, right? If the car's headed straight towards it or straight away from it. Right? So I put those out, but they're kind of finicky. I don't know. Anybody try it. All right, so there it is. So we got the question, we got the measuring tools. You guys good so far? All right, now procedure. The first thing is always just very briefly describe the setup. And it could be just real short. Guys, this is all in one sentence. Set up an incline at a shallow angle above the horizontal for a car to roll down. Boom. That's it. That's the entire setup. And oftentimes that's really all they're looking for. Maybe more complicated experiments, maybe 2 or 3 sentences, but that's all. Just brief description. Okay, well, now I know what the setup is. So give your point if you describe a setup. Yeah, something like that. Okay. Right. So again, these procedure steps are more for this distance versus time. So here. Use a protractor to measure the angle of incline to the horizontal. Record that measurement degrees. Right. So yeah, because you would want to control that angle. So if you mention something about measuring the angle, controlling the angle using the protractor, if you mention something like that, give yourself a point. Oh yeah.
What's the use like of Google?
True. Yeah, because I gave you guys a different way to calculate the angle. You could have done the height and the length of the incline. You got an inverse sine. That's perfectly fine. Yeah, you can do that too. So you didn't have to say a protractor. You could use a ruler or a meter stick. Triple V balance to measure the mass of the car. Record the mass of the car. Of course, this would have been a control for this particular experiment. Something about measuring the mass of the car. You could use the digital scale. That's fine too. With the meter stick, establish a 200 centimeter rolling distance for the car to roll down. So point for application of meter stick. Right. Notice how I'm mentioning how I'm using each of these measuring tools. I use this tool to measure this variable, this tool to measure this variable. That's exactly what they're looking for.
Yes.
Release the car from rest at the top of the incline. Use the stopwatch to measure how much time it took to reach the bottom of the incline. So that'd be I would pick up a point for that for mentioning application of the stopwatch. Right. Okay. So great. That's one trial. Repeat this step 2 more times and take an average of the rolling time. So you guys see where it says 1 point for use of multiple trials to reduce random error. In fact, I might actually want to spell that out. I might want to say to reduce random error or something like that. Because sometimes you're a little fast with stopwatch, sometimes you're a little slow. That's what random error means. And so if you do multiple trials and take an average, then sort of it gets rid of that random error. Okay, so that's always a point. Okay, make sure it was right there. And then, okay, I have to identify what's my independent dependent variable. So step 7 here, say change the rolling distance to, well, a different distance, right? And repeat steps 5 and 6. So the past few steps of like timing it. Do this for 5 different rolling distances. There you go. And at that point, I've identified what's my independent variable. In this case, distance. What's the dependence? In this case, time. And everything else controlled. The mass of the car is controlled. The angle is controlled. Right? Sort of implied there, but that should be the trick. Okay, so that's the entire procedure. That's all they really be looking for something like this. Next category is analysis, and I told you guys this is usually graphs. So guys, all those graphs we put together, that's analysis. So to plot distance versus time. Now, when we did that, let me find distance versus time. You guys remember that created this parabola? Right. We said, well, I probably want to linearize that, or AP would probably prompt you to linearize that. So also distance versus time squared. So both of these graphs would be relevant to analysis. Distance versus time squared, you can very easily create a linear equation out of that. So is that what I said? Because the shape of distance versus time appears parabolic, linearize the graph by graphing distance versus time squared. And I would get a point for each one of those. Distance versus time gets a point. Distance versus time squared, which linearizes the graph, makes another point. Okay. This next point, well, okay, you wouldn't really expect to know this. I put in brackets at this point in the class. I kind of went over this with you guys. That it turns out that the slope of the graph represents half of the acceleration of the car, and I can back that up with my kinematic equations because that takes place as 1/2 a here. Right. Now, by the time May rolls around, you would be expected to know that, but at this point in the class, yeah. Okay, so, right, and then conclusion. So my conclusion is that the distance the car rolled down the incline is directly proportional to the square of the time to roll down the incline. Or more simply, if I just wrote this in equation form, if I wrote distance is proportional to time squared. That this is the same thing. Guys, this sentence and this very short equation say the exact same thing. Okay? Distance is proportional to the time squared. Okay? And that would be the conclusion and pick up a point for that. Right? Right. So go ahead, take a few minutes to score your own using the scoring rubric. Actually, you know what? We're real close to the end of class, so I'm going to do one more thing here and then have you guys, while you guys are scoring this, I want you to point out the differences between how I write these kinematic formulas and what AP gives you on the equation page, which, by the way, are the first 3 formulas on this page. Oh, yeah. Well, write on your own paper. Right? Yeah. Because the scoring rubrics I'm using for my other classes to write directly on your own. Yeah.
Are we turning this in?
Yeah, I'm gonna have you guys turn this in. Okay, so you guys score yourself out of 15. So you've got 11 out of 15, right? 11 out of 15. Now, what I'm gonna do in the grade book is I have a grade column that does not affect your class grade. So if you get out 11 out of 15, I'll put 11, but it's not gonna like bump your grade down or anything like that. I'll have a separate grade column just for the fact that you did it and did the graphs and turned it in. Okay, so do all that. Okay. All right, so yeah, go ahead and score yourselves out of 15 and turn that into the grade tray up here. Okay, in the last few minutes here, I'll show you guys these formulas. So AP writes them like this. They do a little different order. They take the velocity pushed up to is equal to the initial velocity plus the acceleration times time. Okay. Now, yeah, guys, once you have it, just staple it all together, turn that into the grade tray. So you scored yourself out of 15. Yep.
Staple together.
Scored out of 15. Yeah. So, huh?
Like it's in somewhere.
Either that or you can turn the notebook. Yeah, one or the others. Yeah. If it's in a notebook, you can either turn the notebook and I'll get back to you tomorrow, or you can tear it down. That's okay. Right. Yeah. So you check, check the points you got. You scored yourself out of 15. Okay. Now, here I'm looking at how does AP write these formulas. They're in a little bit differently. So what's the differences? Guys, what do you think the subscript X means as AP writes it? It's really tiny here. I just blew it up bigger. It doesn't represent distance. The subscript X represents a what? A direction. You can know X, Y, or Z axes. Okay, X, Y, or Z axes. Okay, here the next one this way. X equals X naught plus V X naught T plus 1/2 A X T squared. Okay. Because eventually we'll be getting into more than one dimension. Okay. But the subscript X right here, like this X and this X, refer to along an X axis, just along one axis, something like that. Okay? Now, guys, look at how I write this formula versus how AP writes this formula, because it's a little bit different interpretation. You see, I just have X for a displacement here, but on AP equations, they write X in terms of exact position. That's why they have final position equals initial position plus blah, 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 blah. Is that? But what if you do this? Because what if you take this initial position and you just subtracted it over? Wouldn't that be like final minus initial position? And that could represent a displacement, couldn't it? Okay. And that's how that's really what my X means. It refers to a displacement. Sometimes it's put a little delta there, like delta X. Okay. Delta X. Okay. So just know what you're looking at and how to interpret it. There's like 2 different ways to write these equations. So this way I do it, this way AP does it. And this final one, they go final velocity squared equals initial velocity in the X direction squared plus 2 times acceleration in the X direction. And then final position minus initial position. Okay. Again, their X values are in terms of exact locations. Right? And when I write it, I just write it as a displacement. So my poster, I just write it X represents displacement. How far is it due? AP writes it as exact locations. Okay. Okay. A little bit different way of looking at it. All right. So we got it. Yeah. Okay. I'm always hoping to fit in more. We have to hit kind of a pop point here because we only got a couple minutes left. So again, go ahead. Make sure you have the scored out of 15. Make sure you got your sprite up, your graphs, your lab table, all turned into that gray tray. I'll give you guys points for that. And we will definitely be taking the next couple of days to be solving a bunch of linear motion questions.